Hello. Can you see the
Yes.
screen?
Yes, sir.
Yes, sir.
Okay. Okay, we are talking about pointers in C++, and these are the topics that I'll be covering in this particular uh, section. So here we already talked about the basics of pointers, use of uh, indirection as well as address of operator, multiple indirections, and legal and illegal operations on pointers. And also we talked about constants in C, and we found that in C++ if there is runtime allocation, runtime initialization of constants are possible, and constants may not be allocated some space until unless we ask for the address of that constant or it is an aggregate constant. So those we have already explained in my second lecture on this pointers in C++. And we found that how this pointers versus or pointer and constants are related. I mean, how we can write or declarations that involves the definite declaration of pointers as well as constants. So it can be a pointer variable pointing to a constant entity, or it can be a pointer constant pointing to a variable entity, or it can be a pointer constant pointing to a constant entity. So there are so all the 3-4 variations we found in our last class, and we started talking about this array, the relation between array and pointers. So we'll continue with, so we have done that one-dimensional array. In this class I'll be continuing with the 2D array, how they are related, how the notion of pointers are related in the declaration of 2D arrays. I'll talk about the memory layout of a C++ program, and this will be the topic. So I'll target this much in today's lecture. Let's see how much I can cover. Okay, so this will be the focus of today's lecture. I skip these parts. This we already found, and the important point to note is here. So the behavior of, so what is important to notice this. So a one-dimensional integer array, if I write or if I try to see that what this, how this A behaves as this A, we found that it behaves like a pointer constant pointing to integer elements, right? Can you recall that?
Yes, sir.
So the reason is how we verified that, because if you try to write A++, it never permits you to do that. So this A behaves very much like a constant pointer, and A is also a pointer because if you display the contents of A or ampersand A, it just gives some address. So this is a pointer, but this behaves like a pointer constant. However, the pointer arithmetic is applicable. If I write A+1, A+2, it applies this pointer arithmetic. So how many bytes it skips? So we have to, for that we have to see that what this pointer constant A actually points to. So it points to these blue boxes, these blue integer boxes you can think of. So if you write A+1, it will skip one box and it will try to point to the next box. And if you again do A plus, so if you write A+2, so it will be pointing to this particular box. So that is as if you are asking to skip two boxes like this. Okay, so that is what we found, and we also found that A plus I. So A means what? A is the starting address of the first box or the 0th box. So it's a one-dimensional array. It's a collection of integer elements, or these blue boxes. It's a one dimension collection of it. So this A means it is basically pointing to the base address of the entire block. And if I write A plus I, as per the pointer arithmetic. So it will be shifting or skipping I number of boxes, maybe one box or two box or three box like that. And but still it will be outside the blue box, maybe here or here or here, depending on that. So this basically outside the box means as if you are specifying or you are denoting the address of that particular box. So that's why a plus I is equivalent to writing as ai ampersand. Okay, so this is the address of the ith element. And if I simply put an asterisk, this means we can consider it for simplicity that as if you have broken the seal of this box and you are now able to see what is inside here. Okay, so these you can consider that all these elements are box wrapped, and if you put a asterisk, you have opened it and you can see the contents now. So a plus I asterisk is equivalent to ai, because ai we know that through this we can access the ith element of the array. So this is, these we call as the array index, the array notation, and this we can call it as pointer notation. But both are the same, and it really doesn't matter. So what kind of allocation it is static allocation. So this is, we'll come to it in details, what how the dynamic allocation differs from it. So in case of static allocation, even though it's a static allocation and there is no mention of pointers during the declaration, but you see when you are writing asterisk a plus 0 or asterisk a plus 1, the compiler can interpret these notations, and I mean it is easier for it to interpret rather than the array notation. So no matter what the way you have declared the array, both the array notation and the pointer notation can be used uh, uh, as you wish. Okay, so there is no restriction on that. And in fact, whenever we write array notations, you can assume that internally the compiler translates it basically to the pointer notation, which is more basic and which can deal with addresses, right? Is that okay? So this much we found, and here we, if I want to assign the value of a, the type of a is int asterisk, so I can declare a pointer variable int asterisk, which is a pointer to integer, so that I can assign the value of a, and I can accordingly increment p or access through that p, I can access the elements. So let's come to the two-dimensional array. So how can we interpret a two-dimensional array? What it is? Can you read this? How can we read this array? What is A? A is a 2D array consisting of
2 rows and 3 columns.
2 rows and 3 columns. Okay, so this first one is the number of rows and second one is the number of columns. So this is the number of rows, number of columns. Now the point is, so what is this? So if we visualize it in a logical view, so this is how you look like. It's a planar or two-dimensional arrangement of elements, integer elements, right? So there are 2 rows, 3 columns. So what is this? This is RAM. So RAM we have preferred to view it as a it's a sequential collection of locations, right? That is what RAM is. So you are trying to you are having a 2D planar arrangement of elements. So if you want to store these elements in a sequential collection of locations in RAM, so you have to first get a mapping of this. You have to first find a sequential ordering of these elements. So what can be the possible sequential ordering of this, of these elements? So this is a programmer's view, right? But when you are, when the compiler wants to store these elements in the RAM, it need to define some sequential ordering of these 2D arrangement of elements. So what can be the possible ordering?
So row measure and column measure.
Row measure and column measure. And what row measure is? First you take 1 by in the 0th row, so it will be 2, 4, 6. Then you come down to the second row, it's 3, 5, 7. So it's basically 2, 4, 6, 3, 5, 7. So this may be one option. What is the other option? Other option is a column measure option. So these are all thoroughly discussed in the data structure class, but for completeness I just want to review it once again. What is a column measure? Column measure means one by one you think of the column elements are stored. So it's 2 3, and then comes a second column 4 5, and then comes 6 7. So it's basically this one, right? Is that fine? So this is trivial. So which sequential order is actually used to store the elements? So there are two possibilities, this or this. So which one do you think is actually followed while storing the elements in reality in the RAM?
The row major.
So this is the default one, right? That also you know. So if you want to force it to column measure, you have to write a piece of code, and then but otherwise if you just declare a 2D array, so it will be storing in row measure because that is a default. So there are other possibilities also. Can you find out what are the other ways of doing things? There can be diagonal measure also. You can also try to define some kind of this thing. So this diagonal, then this diagonal, like this. Okay. So this row measure is something that is actually the default. Okay. So if this happens, so what will be the actual allocation in the RAM? Do you agree with this?
Yes, sir.
So all others, can you see? So now you see that. So what is this? What does this mean? And this mean? So this means the row 0, and this means the row 1, right? Or first row or second row, whatever it is, row 0 and row 1. So basically, as it says, so you store all the row 0 elements in that order, and then followed by the row 1 element. So these are row 0 and these are row 1. Okay. So now instead of so we can extend that the previous understanding that if it is a one-dimensional array, it's a collection of blue boxes. Now I say that these blue boxes within a particular row, so each of these elements within a particular row is basically packaged, or it is put enclosed within another green box. So this row 0, all the elements are packaged in this green box, and the row 1 also, all the elements are packaged in the green box. So there will be one green box wrapped within another bigger box, kind of. So this is the green boxes. So these are the row boxes, kind of thing. So here for this particular array, so 3 column boxes, the blue boxes, are packed within a row box, that is a green box, right? So now how can we read this array then? So A is an array of, it's a collection of, how can we state it as? It's a collection of what? What he points to? Collection of Can we say that A is a collection of green boxes?
Yes, sir.
Earlier what we told that so in a one-dimensional array, the array is a collection of those blue boxes. So blue boxes are basically raw integers. Now we say that A is a collection of green boxes. Now each green box consists of again multiple blue boxes. That is fine. But how I say that A is a collection of green boxes, right? So here, because there are 2 rows, so each row corresponds to a green box. So there are 2 green boxes. If you have got 5 rows, so it will having 5 green boxes, and each then encapsulates or packages several number of blue boxes. That is what it. So that is how we tend to view it. There is no such box or something like this, but for ease of understanding. So now if I come to this, so this is, you see, this is the integer array A of size 3. So say this is what it means. So this A is a collection of, it's a collection of blue boxes, and this B, it's a collection of green boxes. It's basically the rows that we all know. Okay, so the point is, if I write here A means whatever is the address, this is copied from that the run while I ran the program. So that's why, so this is the value of A. This is the ampersand is also the same. You see, both are the same because both means the same. Now this a plus 1, a plus one means what will be the pointer arithmetic here? Because it is pointing to these blue boxes, so it will skip one by one the box. So it is basically one integer. In reality, how much it occupies? 4 bytes, right? So it will be C0 plus 4, it will be C4. Is that okay? A plus 1. Is that fine?
Yes, sir.
So what about this one? So if I write here B, so B, if the B is this and B ampersand B is this, both will be the same, right? Now if I write B plus 1, if I write B plus 1, what do you expect? What will be the incrementation? So B is basically, B or ampersand B is pointing to this green box, right? The address of the first green box. If I write B plus 1, what do you expect? How many locations it will skip?
4, I guess. Sir, it will go to 2014.
Yes. Somebody was telling 4. Why it will be 4? That's why I'm repeatedly telling. It's a collection of green boxes. Say you have got 4 green boxes. You are now outside the first green box. Now for you just recognize green boxes. You don't recognize whatever it is there inside. So if you write B plus 1, what do you think will be the incrementation? From 2008, it will it be 2010? Will it be 2010? It will be 2014, right? So from here you are skipping the boxes, right? Because you know that I am pointing to boxes. That's all. And if you again increment, it will be pointing to somewhere here. But here, if it, so this A, I mean, this is what about the B, and this A, because it points to the blue boxes, if you increment, it will be pointing to this like this. That's why I write collection of blue boxes, and here it's a collection of green boxes. Are you getting things now?
Yes, sir.
So if you view it like that only, then you will be able to correlate. Otherwise, it might be it might look confusing. That's why we can consider that these are packed within boxes like this. Okay, but there is no such packaging or these things that takes place in the memory. But logically, this thing actually happens. So if I write B plus 1, but the thing is, the main point to note is B plus 1, B plus 0. So what is B actually? So what is A here actually? So A is basically nothing but A plus 0, right? A plus 0 and A is the same. And what is ampersand A? Ampersand A is what? This is same as A plus 0. So this is A plus 0, this thing. So both are same, the value is the same. So here B means what? B means actually B plus 0. So nothing you are adding, so you are still here. So ampersand B is also this, and B plus 1 means you are basically, it will be displaying 2004, but logically it means you are still outside the green box. So can you see that to reach to this particular 3, if you are outside this green box and if you are displaying here say 2014, to reach to this 3, to read the value 3, how many unpacking you need to make?
So 2.
And each unpacking actually in programming terms, what it means actually, what operation you, what operator you
Indirection.
need? Indirection. So how many indirection you require?
So 2.
2 indirections. But in one dimensional arrays, you just need one indirection because it's just visualized as a simple box. But here box are within boxes, so 2. So let us now come to this point. So it's a collection of 1D. So you can say that it's a collection of 1D integer arrays. A 2-dimensional integer array is basically can be thought of a collection of 1-dimensional integer arrays. So this is the first integer array, second integer, like that. Okay. So that is how the logical interpretation is. So here now do it fast. Now tell me what the values will be with respect to this example. What is A?
2008.
What is ampersand A?
2008.
A plus plus?
2014.
A plus plus?
Oh no.
No, sir.
It will be an error.
Yeah. Don't make the mistakes.
Yeah.
Again and again. So it will not be, it will be prohibited. It will not be compiled at all. Because again, like that one-dimensional array name, this A also behaves like a constant. It's a pointer, but it behaves like a constant pointer. What about this A plus 1?
2014.
2014. Yes. Any other doubts? What about this one? A plus 0?
2008.
14.
No, A plus 0. I am talking about A plus 0. What is the value of A even after this statement? What is the value of A? You have added 1 to A, but did you modify the contents of A here?
Oh, sorry, sir.
No, sir.
Okay, so A still remains the same, 2008, but you said that I want to just add pointer arithmetic 1 to it. So it becomes, because it is pointing to this row boxes, so it will basically, so here the pointer arithmetic will be, size of A3, right? Kind of, it's a row box size. That is how it gets incremented, right? Plus this. So what is A plus 0 as simple A plus 0? It will be 2003. Now if I write A plus 0 whole of asterisk, then what it means?
2.
How can it be 2? 1 asterisk means where you are. One asterisk means where you are. So this red one means you are here, right? If you say it is here. If I give a asterisk means where you are.
Sir, the green box.
So you are basically, so then this means if I use a blue, so you are basically here, right? So that means what? You are outside the
Scope.
so you are you are inside the green but still outside the blue, right?
Yes, sir.
Now if I write here, you see asterisk A plus 0 plus 0. So first of all, what is the value here? A plus 0 asterisk, what is the value?
Sir, the A0 array.
No, I mean, what is the value? What value it will be displayed here? That is my question.
2008.
It will be 2008. Why? Because you see, so 2008 is what? 2008 is the address of the 0th row. I mean 0th row, right? The entire 0th row. But 2000 is still is also the address of the 0th element of the 0th row, right? Is that fine? This is the address of. This is also the address of the first blue box within the first green box, right?
Yes, sir.
So what will be the value here? So this value is 2008. Now if I give, so if I add to that value just a 0, what will be the value displayed here?
2008, sir.
So is there any change here? Asterisk A plus 0 plus 0. So nothing I have done. So do you think any changes will be here?
No, sir.
No, sir.
It will be still be 2008, right?
Hello?
Now I make one more asterisk. So the whole of it, then another asterisk I give. Then what do you think? What will be the case?
2.
So now you are breaking open this also, and you are here now. You are here means you are free to see what it is inside, right? So now what will be displayed here?
2.
The value 2 here.
Hello, sir.
Yes.
Sir, if it was 2009 or 2010, then star A will be 2008, na?
Which one? A of?
If A was 2009 or 2010,
A was 2009 or 2010. Yes. Then
star A plus 0 will be 2008.
no. So in what context you are telling? So what I mean, so what is the difference between these two? This means A plus 0 is basically the address of, you see, this is the, let me write it first. So this is the address of, what is the interpretation? This is the address of the 0th row, right? This is what it means. This is the meaning of it. And what is the meaning of it? This is the address of the, you see, this and these are the same. So what does it mean? This is the address of the zeroth row, zeroth element of the zeroth row. Are you getting the point? This is the address of the zeroth element of the, so this is basically the address of the blue box, the first blue box in the first green box. This is the address of zeroth element of the zeroth row. Are they different?
No, sir.
If you consider sequential allocation, the zeroth row will come before the 1th row, which will come before the 2th row, like this. And within the 0th row, you will have the 0th element of the 0th row, then will be the 1th element, because you have followed row measure. That is the default, right? So a plus 0, if it is 2008, a plus 0 asterisk, or writing asterisk a plus 0 plus 0, both are the same, will also produce the same output, right? It will be 2008. Although it is the same output, but you say that meaning, so the meaning is, interpretation is different, because now if you write this, means you are one step ahead of getting the access to the integer value. Are you getting the difference here?
Yes.
Everybody, are you getting the difference?
Yes, sir.
The thing is, value the same. Value same means please switch off the mic. Somebody has switched it on. So values same means the interpretations are not the same. But why the values are same? That makes sense, right? And this means you have used the first one to break open the green box seal, and the second one to break open the blue box seal. And once you have done that, you can access the element here. So this much is enough to understand the rest of the concepts of the array and pointers. So what will be this value? Now tell me. A plus 1.
2014.
2014.
Right? There is no doubt about it, right? So if it is a plus 1 asterisk, what will be the value?
2014.
2014.
So when I wrote a plus 1, simple a plus 1, I was here outside, waiting outside. If I give asterisk, means I have just opened the door and gate, and I have inside here. I am inside here. But still, if I say what is the address, I am still the 2004, right? So this is 2004. Now, if I give this much, what is the value?
So why 2004?
It's
Sorry,
2014.
14.
Oh,
Okay.
So now if I write this, there is no difference here. So
Yes,
just
sir.
I added. So adding 0 means nothing else. Neither I have, so there is no change. Neither I have got one level inside or outside, and I am just standing there itself. And if I write here, means I am here.
So 3.
So it will be giving 3. So in the similar way, if I write, okay, so yeah. So what is this? A plus 1. What is a plus 1? It is 2014.
2014.
2014. Now if I give here, so now look into this. So a plus 1 asterisk plus 1. So a plus 1 asterisk means I am here.
2020.
So then I write, instead of 0, I just add 1. So 1 means now you are already inside. So see the difference. If I now increment, if I say add 1 to it, it will be adding, and I'll be taking me here, right?
2016.
So it's basically 2016. Now if I give a asterisk here, one more asterisk, I'll be here inside, and I'll be getting access to this value 5. Is that fine?
Yes, sir.
So this is very simple, but once you know this was very simple. So what it is actually in the array notation?
Sir, why is the third output 2016? Sir, could you repeat that again, sir, just once?
What is a plus 1? A plus 1 is
2014.
A is here. So follow the steps. A is here. You are here outside the green box. Plus 1 means, because you know that there are green boxes only. You don't know what is inside. So you will be skipping this much here,
Yes,
right?
Yes,
Now
sir.
you are here. You give asterisk. You are here inside. Can you see the pointers?
Yes, sir, yes, sir, yes, sir, yes, sir. Now
It
got
is
it.
here. Now plus 1. Plus 1 means now you can see only blue boxes, right? So if you plus 1 means you will be here.
Okay, sir.
And then again asterisk means you break open and you are accessing this value. So in array notation, what is this? What is this? I am accessing the 1th element, right? The element in the first column of the first row. Is that fine? So this is equivalent to this. Hello?
Yes, sir.
What about
Yes,
this
yes.
one? In array notation, what do we write this? See the interpretation as right.
Ampersand A11.
It is ampersand A11 because you know the interpretation. This means we are talking about here this point. So this point we are mentioning that we are just trying to. So this is the address of the first. So it is basically the 1th because it is basically the second. So 1th element of the 1th row, right? It's address of the 1th element of the 1th row. What about this one? How do I write it in the array notation?
Ampersand A1.
Address of
ampersand A on 1. Sorry, A on 0.
Ampersand
10.
A1. And what about this one?
Ampersand A on 0.
No, I don't A10 because what does it mean? There is no asterisk, right? So you are outside the green boxes. So if you are outside the green boxes, can you talk it? So this means you are talking in terms of the blue boxes, right? So this means you are talking about the blue boxes. So if you are outside here, can you see whether blue boxes are there or inside or not? So what should be the interpretation here? It should be interpreted as this much.
A1.
So it's the address of the 0th row. That's all.
A1.
So
Sir, A
I'm sorry.
on
A1 will be there.
Yeah, this will be A1. Yeah. Right? Because when you are here, you cannot talk about, so there is no second subscript. You cannot see that. But the values are the same. That's fine. Is that okay? Hello?
Yes, sir.
So now, in this case, so what you can write, this is equivalent to writing A of I ampersand, right? This is also, this will be A of I. Then what is the interpretation? This is an address, right? This is an address of AI 0, right? What is this? What is this?
AIJ.
AIJ? Is it an element or address?
It's an address.
One ampersand means one asterisk means it's just an address. What about this one?
That's AIJ.
AIJ. Okay, so they are exactly equivalent. There is no difference at all. So no matter even if it is a static allocation, if you write these pointer notations, it will, I mean, the compiler might be obliged to you, okay, that it need not have to carry the entire translation, right? If you write it, maybe it will be translating it back and then interpreting it. So it says that I'm happy that you have already done it for me. Got the point? But they're exactly the same. You are talking about in a memory language, or I mean in a lower level language kind of thing. But here it is more in a logical way you are telling about. So when you are writing AIJ, so this means you are talking about in these terms, in the schematic view. But when you are talking about these things, that means you are talking in terms of you are aware of the memory allocation and you are talking about those terms. But they are exactly the same, and it doesn't matter how the allocation took place, whether it is static or dynamic. Is that okay? But if I write A++, not allowed. And this one we have already mentioned. So here A behaves as, what is the behavior of A? How can we write it? A behaves as
The pointer to pointer.
First of all, A behaves as a constant, right?
Yeah.
A behaves as a constant. Constant pointer to what? Constant pointer to integer pointers.
Yeah.
Constant pointer to integer pointers. Because a row box is basically a one-dimensional array, right? It's a pointer to one-dimensional integer arrays. And how a one-dimensional integer array is represented? It is interpreted as integer pointer, right? The address of a integer one-dimensional array can be stored in integer pointer like this. So this A is a constant pointer. A is a constant pointer pointing to integer pointers. Got the point? This is the behavior of A. Or in other words, you can write here int asterisk asterisk const A. Is that okay? Hello?
Yes, sir.
So if I would like to store the value of A, if I would like to store the value of A, where A is in some P, how should the P be declared as? Some pointer which is equivalent of or is capable of storing the contents of A, or I mean whatever A means. Your voice is breaking. I don't know whether there's a problem in my connectivity or yours. Anybody else? Hello?
Sir, integer star pointer.
Pointer to a pointer, sir. Sir, integer pointer to a pointer.
Right? Because that is what it means. So the only difference is A was behaving like a constant, but P is just a variable. That's all. So you can store the some constant's value to a variable, and through that you can modify. That's not a problem, right? So now, so using this P, you can still do the same thing as we did it earlier. Is that okay? Up to this series, is it fine?
Yes, sir.
So are there any doubts? I'll switch to the next part. Is it completely okay with all of you?
Yes, sir.
Yes, sir.
So
Yes,
things
sir.
will be things will be incrementally tricky. So if you are not getting things right at this moment, so rest of the things will be, it will be completely gone. So just make sure that you got this point. These are very simple things, but because you are getting these things probably for the first time, you might mess it up. That is the problem. It's nothing too difficult. It's not quantum mechanics, so it's very simple, but the notations you have to interpret the notations and all this. So let us come across some typical pointer declarations, right? So what is this? This is an integer. It's a integer variable. What is this P1? How I read this? P1 is a pointer variable pointing to a integer variable, right? This is what it means. That is how I read. How I read P2?
Pointed to an integer.
Pointed to an integer pointer.
No, P2 is a pointer. P2 is a pointer pointing to a pointer to an integer, right? So this way you can say. I mean, this helps you to read. So P1 is a pointer variable because there is no constant written here. So P1 is a pointer variable pointing to integer variables, because there is no constant here also. So this P2 is a pointer. There is no constant keyword here. So P2 is a pointer variable pointing to. So this P2 is a pointer. There is no constant. Okay, it's getting. Pointer. Okay, it's getting. So P2, there is no constant keyword here. So P2 is a pointer variable pointing to pointer to integer or integer pointers, whatever we use call it. What is P3? P3 is a pointer variable because there is no constant pointing to pointer to integers. That is how you can read it. Is that okay?
Yes, sir.
Yes, sir.
And this makes sense the way we discuss the whole thing, and this means multiple indirections. So this part is all done. Now let's come to this part. So what I have done in the first line, A14, A23, A32, what are these? What are these?
Sir, array elements.
Now don't make such comments. What is this? A14, A23, A32. Are these elements or what? What is this A1? What is A2? Or what is A3?
1D arrays. 1D arrays.
1D arrays. It's 1D arrays, right? These are 1D array declarations. That's all. So that what happens? Simple things becomes seems to be. So that is what it means. I mean, it's shown here because it's basically too many notations that comes. Until unless you keep using it, you sometimes feel confused. Now, and what is this B1, B2? B1, B2s are
2D arrays.
2D arrays. That's simple.
2D
And these are not
declaration.
initialized. These are statically allocated. That's all. Now, what is P3? What is P3? How I read P3?
Array of pointers to integer.
What is this P3? P3 is, first of all, P3 is an array, right? Array of size 3. What it contains? What are the elements of that array?
Pointers.
No, what type of pointer? So P3 is an array of
Integer pointers.
Array of 3 elements, array of size 3, containing integer pointers, right? Integer pointer variables. P3 is a array of 3 elements containing integer pointer variables because you have not used the const keyword here, right? So now if it is so if I would like to initialize P3, what can be the initialization here? So which of these arrays addresses can be initialized to P3 0 or 1 or 2? What can I write here? Tell me fast. Don't take so much of time. I have so many slides.
A1, A2, and A3, I guess.
It's fine. Is that okay?
Yes, sir.
Everybody agrees? All of you do you agree?
Yes, sir.
Yes, sir. Yes.
And you can, if you want to make it more clear, you can write this also. That doesn't matter. So what it means, and see the figure now. So this is P3, right? So P3 is an array of 3 elements. That is what it says. And the elements of this array are integer pointers. So that's why each of these elements are integer pointers, right? And after this initialization, so what are these? This is A1, this is A2, this is A3. So A1 is of size 4 integer array. A2 is a size 3 integer array. A3 is a size 2 integer array, right? Now, what you said in this single statement, you have assigned the address of A1 to P0, P30, address of A2 to P31, address of A3 to P32. So that is how the schematically the whole allocation. So this will be interpreted as this one, right? Is that okay?
Yes, sir.
Yes, sir.
All of you. So how can we write this one? So what is this P4? How can we read this? P4. What is P4?
Sir,
Each of type. P4 is an array of 2 elements. Now what it contains? Each element
pointer to integer.
It's a pointer to integer. Right? So what is a pointer to integer? So it's B1 and B2. So B1 behaves like a pointer to integer, right? Though it's a constant, but the contents of B1 or whatever value it displays, it behaves like a pointer to integer. Is that fine? You just now mentioned.
Yes, sir.
And B2 is also like that. It's a pointer to integer. So if I would like to initialize this P4, what should I write? With the addresses of B1, B2, what should I write?
B1 and B2.
Is that okay? And if I do so it will be looking like this. So what is this? B1 which is basically a 4x2 matrix or 4x2 array, and this is a 2x2 array. So the address of this, the base address of this will be stored here, the base address of this will be stored here. So this is not a memory layout view, but this is a schematic view, right? And this schematic view, so this is what has been done. So this statement actually performs this. And what is the type of this? What is the type of elements of P4? This is int asterisk asterisk. Okay, and these are int type. Up to this, is it fine?
Yes, sir.
All of you? Hello?
Yes, sir.
Yes, sir.
So this is okay, right? P1 to, so what I can assign here? So just now I did it. So it is, if I write address of A1 and address of A2, will this work, this part?
Yes, sir.
P2 is
Yes,
a
sir.
array of 2 elements, each pointing to, each of them they are capable of pointing to integer pointers, right? So is that okay?
Yes, sir.
Now what about this one? How to interpret this one? I have made a parenthesis here. Does it make any change?
Yes, that means
Means what?
we can guess P3 pointer. With,
Hmm?
we can guess P3 as a pointer. P3 is pointer P2.
No, forget about P3. I'm talking about this P2. How can we define P2? What is the interpretation of P2? First of all, is it valid? Is it a valid? This is valid, right? So this, let us accept that this is valid. Now try to interpret this. So if I write, what is P2? P2 is a, what is this? P2 is a, now when you read this, so because of this parenthesis, you should read this part first. What it says? What is this? P2 is a, P2 is a,
Pointer.
it's a pointer variable, right? Because there is no constant keyword here. So it's a P2 is a pointer. P2 is a pointer variable. To what it points? What
So
it
it points
points?
to the array address itself, so the entire array address.
Yeah, that is fine, but to what it points? It can point to any integer, one-dimensional integer array of size exactly 2. That is the point. Are you getting my point?
Yes, sir.
Yes, sir.
So that's the difference. So this is P2. P2 is just a single variable. That's why it is single variable. It's a integer pointer. It's a pointer to integer of type. But the space that it points to must be a group of 2 integers only. Only this much. And if you are trying to ask P2 to point to a group of 3 integers, I mean array of 3 integers, it says I can't. Is that fine?
Yes, sir.
So how can I write P2? P2 so what should I write? What is P2? P2 is a pointer variable capable of pointing to any, because it's a variable, any 1D integer array, any one-dimensional integer array like this of size got it? Is that okay?
Yes, sir.
Yes, sir.
So what about this one? How do you read P3?
So P3 is an array of containing 3 elements.
It's a array of pointers.
Yes, sir.
Array of 3 elements. Each of them they are pointers to
And
pointers
1D
to
array.
integer of size 2.
pointers to this type of
And
this type
1D array.
pointers to 1D integer arrays of size exactly 2 elements.
Yes, sir.
Pointer variables, because there is no constant keyword used here. If we put a constant here, it will behave like a constant. It's an array of pointer variables, array of size 3, each of which is capable of pointing to any 1D array, int array of size elements. Is that okay?
Yes, sir.
So you can see here we have so out of these 4, it can point to A1, A3 and A4, but it cannot point to A2. So now P3 it's now pointing to A1, A2, A4, A3. Sorry, it is not A2. It should be, there's a mistake here. A1, A3 and A4. Maybe it is A4. Okay. Is that fine?
Yes, sir.
Yes.
So this makes sense, right? So now we can write this and we can write this. Okay. So what about this one? This is in terms of a 2-dimensional array. So now what is this P1? P1 is a
So it's 2D array of pointers, integer pointers.
It's an array of integer pointers, but it's a 2D array of integer pointers, right?
Yes, sir.
P1 is a 2D array of integer PTRs, right? What is this P2 here?
Sir, it's an array. It's a pointer to any array, a 2D array with the same parameters as 2 and 3, sir.
P2 is a pointer
To any 2D array with 2 and 3
to any 2D array of size
2 plus 3.
exactly 2 cross 3. And what about this one? P3? P3 is an
array of
Array.
integer pointers.
So this is pointer
to a
variable.
2D array.
This is a pointer variable. It's a array. It's a pointer array of 2 elements, each of which can point to two D arrays of size exactly 2 cross 3.
Hello, sir. Sir, can P2 point to any array lesser than 2 cross 3? Means 1 cross 1 or 1 cross 2?
No, it cannot. That's why I am mentioning exactly. I'm specifying this one. Exactly this one. There is no relaxation here. What I showed here. Here you see. This is 2 cross 3, but P2 cannot point to this 2 cross 2. That is what I shown. Hello? Got it?
Yes, sir.
Yes, sir. Yes, sir.
So is this fine? These two allocations. So this schematically it shows it like this. B1 and B2 these two are compatible. It could have pointed to B4 also, but it cannot point B3. So B3 the size, as we have put the restriction, it cannot do that. Is that okay?
Yes, sir.
Any question? So keep it in mind, we'll be using it very soon. Okay. So now let's take a break on the pointer notations and all. So before we get into the details of the rest of it, so now from now on, instead of this view, what is this? This is a view of the RAM, right? So instead of viewing RAM like this, you would like to view RAM as a collection of segment or block of memory locations. So the RAM can be considered with respect to a particular program. When we run a program, from the programmer's perspective, we should view RAM not as a sequential contiguous collection of locations, rather as a collection of segments, or you can say it's a block of memory locations, and each block can be of variable size. So it is something like so those who are outsiders, they will feel that okay, all the students, they are staying in the same hostel. I mean there is a hostel, there is something like a very big hostel where all the students of NIT Durgapur is accommodated. So it's a capacity of 5,000 or 4,000 students. So all are accommodated like that. But that is not the actual true case, right? So what actually happens? So instead of a single very large hostel, we have got, say, different hall 1, hall 2 like this. This blue hostel, this blue hostel, blue hall, yellow hall, green hall, and all this orange hall like this. So what are the purposes of these halls? So there is some logical cohesion, right, about the elements that they store. Is that why it is so? Hello?
Yes, a similar characteristic, like similar people of the same year stay in one hall. So
Yes. Or maybe in our case, sometimes we have got a foreigners hostel, no matter what his year is. So foreigners, they are paying more and they will be given more privilege, something like this. So so they are having a better, maybe a better condition hostel. I never went into inside, but let us assume that. Or again, we have the restriction like girls and boys, they cannot stay. So there are many ways of creating this division. It may be year wise, it may be based on the gender, it may be based on which country you belong to and all this. So this is some logically, so this was quite fine, but so because of the logical correlation, the memory management module or the operating system provides a view something like this rather than this one. So it will be providing is like this, and each of these block, so it's a kind of a chunk of locations, which is a block, and these are block, these are block. So there are 4 blocks, and each C++ code is organized in exactly 4 blocks. Can you name? And here the block is basically known as a block is known as a segment. So can you name the segments? What are the segments exactly? What are the segments a program is organized in memory, in which the contents of a program, and when it is running, it is called a process. The process's memory is organized internally. There are exactly 4 segments. Those who are, good coders, or so they might be knowing these names because they will be using it often. I know many of you are having good ranks in online sites and all. So what are these segment names called?
partitions.
Yes?
Partitions, sir.
No, partition is something completely different. Specifically segment. Have you heard about, you may not have used it yet, but have you heard the names? Heap segment. Sometimes it says a heap segment. It So you have to increase the heap segment size, otherwise the program will hang. It's taking more. Heap segment, stack segment. Have you heard of it? Code segment, data segment. Heard of these terms?
Yes, sir.
Anybody heard these terms?
Yes, sir.
Okay, good. So can you tell me what are the implications? So in a heap segment, what type of values corresponding to your code will be stored in the heap segment? Like that, the foreigners will stay in the yellow hall, something like this. So heap segment, what type of values will be stored? What type of memory, what type of variables or constants will be stored in the heap segment? Tell me quickly, because I've got many more slides. So these are very simple things. It should have been taught in the first and second semester, but I understand there is a time constant and there are a mix of all the departments. So that is the reason. Earlier you used to have a CS students only, the class. I mean, the C class also is taken only for the CS students separately, and electronics separately. That was what we used to have long back. So then maybe the way of teaching also was different, and those days it was only a batch of 40 students, and now it has went up to like almost 4 or 5 times. I'm talking in term it is the time of 1997-98, almost more than 20 years back. We used to take classes of 30-40 students of CS. Okay, so now can you tell me what is the purpose of heap segment? What kind of data variables it hosts? What kind of storage? Whenever
The
yes.
trees.
Hmm? What? Just tell me.
One
Hello?
is for static and one is for dynamic.
Yes, so
Heap
heap
is
is
for
for
dynamics.
dynamic. So whenever you call malloc or calloc, okay, so whenever you call malloc or calloc for some memory, because you are asking for some memory, dynamically allocated memory, so that memory will be allocated from the heap segment, right? So there's a group of locations which will be labeled as heap segment. It's a block, and that from that block only you will be, whenever you call malloc, you will be getting space from that. Now if you keep calling malloc multiple times, and if it gets exhausted, the heap segment has no more space. Even though you have got some space in the other segments, you will not be allowed to do that, right? So if the foreign hostels, it can accommodate say only 50 students, and if the rule says that they cannot stay with the normal like with the Indian nationals, so beyond 50 students they will not be allowed to take admissions, right? That is something like this. So heap segment is meant for allocating space which is requested via the malloc, calloc or free operator. I mean, sorry, the new operator that we'll learn in this class. What about the code segment? The name itself suggests that. What is the code segment purpose? Hello. What is the purpose of the code segment? Can you guess? The name suggests itself.
So it stores instructions.
Yes, the instruction means when you compile it, you create basically the binary object. It's
Machine code.
right? The machine code. So the machine code is actually copied in the code segment. So the actual program that you are running, the machine code of that program, the object code of the program is actually stored in the code segment. But that is, you can see that like it is sufficiently large. But again, there are other details, I think, which you will not be able to, it will be too complicated to discuss about it. So your code segment, if you have written a code, a raw code of say for example 1 GB size, or I mean it's very difficult, but again let it be 1 GB size. Even if the code segment is like say 100 MB, it can run it. So what happens actually, the memory, so the entire code is actually stored in the hard disk, and even though the code segment has got can accommodate only parts of it, so in the virtual memory organization, parts of the code from the secondary space is basically swapped in the code segment, and is swapped back. So the memory management module handles it so efficiently and fast. So we don't have to be bothered about the limitation of the RAM, because RAM these days are how much? Say maybe 4 GB, 8 GB RAM, or maybe 10 GB RAM. But you can run applications that spans like several GBs, right? 1 GB or 2 GB size you can always run. That is not a problem. But whenever you are running an application or a process or a program, the whole program is organized into 4 such segments: heap segment, code segment, data segment, and stack segment. Let us assume that right now the entire thing is stored instead of complicating the whole thing. What about the data segment? Okay, what about the stack segment? What kind of variables it hosts?
Statically allocated variables. Static allocations.
Not static. This is purely local.
Function.
Local.
Functions.
Anything that is local to a function, maybe main or maybe some other user-defined function. So anything that is local to a function but non-static, specifically non-static local variables are stored in the stack. What about the data segment? What is left now?
Statically allocated variables.
Yes, static variables. At the same time, what is left? What is left? The global variables.
Constant.
No, the global. The global variables and the static variables are stored in the data segment, right? Now constant is not the problem, because constant, now I'm talking about variables, but constants also the same thing. If it is a local constant, it will be stored in the stack. If it's a global constant, it will be in the data segment. Okay, like that. What it summarizes: the heap segment. This dynamically allocates. This is meant for dynamically allocated space. Will be requested and it will be obtained from this heap. The code segment, the binary of the executable code, will be stored in the code segment. The local variables, non-static, will be stored in the stack segment. And any static and global variables and or global variables are stored in the data segment. Is that fine?
Yes, sir.
All others, I mean, those who tried to answer and those who are not aware of these segments, have you got this? I'll illustrate with one example. So is that okay? Fine. What is the purpose of the segments and why the segmentation is required? Why it is required, you will not be able to appreciate right at this moment. But this is so let us just understand that this is how it is managed. Memory is managed by the operating system. And for each program, you have got a separate heap. So if I'm running 3 applications, so for each of the application, you will have a bunch of these and a bunch of these like this. Got the point? It is not that in my heap, say so both of are the users say logged in a particular machine and running our applications. So your dynamically allocated space will be obtained from your heap, and mine will be from my heap. I mean from different. So application specific, there will be a group of these 4 segments. Is that part fine?
Yes, sir.
So let's come to this. So this is a very simple code. There is nothing too much of details. So what is this? This is a what kind of variable it is?
Global variable.
What is this?
Global static function.
What about this one? This is within the function nested. Within the function, this is what? This is
Local.
what about this one?
So
Local static
function.
Local static. You have to, because I'm distinguishing between global static and local static, right? And what about this one? What about this PF? It's a variable. What type of variable it is?
Local
Pointer, that we know pointer variable, but what it is? It is a local variable, right? What about this one? This is local. This is what about this one? PM. This is local, right? And here, what are these? These are dynamic allocation requests, right? This is dynamic allocation requests, because we are calling here malloc. I cannot draw it here. Okay, so now as it shows this this yellow marker, if I am executing this statement, I have executed this much. I mean, I am here now. So what kind of allocation will take place? So we have got, so corresponding to this program, we have got these 4 blocks, because every process requires 4 blocks: code segment, data segment, heap segment, stack segment. As you can see, so I basically copied this here. Okay, but obviously in binary 0011 like this. The whole code in binary is here entirely. When I am here, because it will start from main, when I am here, is there any request to the heap? Is there any dynamic allocation took place till this point? Any dynamic allocation that took place, because you have executed this and this much?
No, sir.
So till this point, what will be the allocation that will take place here? So this local and local, where it should go? LXM. So local of main, local in the main, and this is P of main, the pointer in the main. So these are local. So where it will be allocated the space? Where from? Just now what I mentioned, these locals will go
Stack.
the stack, because they are non-static, right? This local non-static, so they will all go to the stack, and this is the stack. So stack grows in this side. So LXM, it has been initialized to 1 PM, and what I say, PM is pointing to LXM, right? So this will be a pointer, so it will be storing the address of here, and it will be like this. So up to this, is it fine?
Sir, why the variable lxfn is non-static?
Which one? LX?
lx underscore fn.
Where it is? Here.
Yes, sir.
Non-static means I have not used the static keyword. To make some variable as static, you have to write it as static, right? You have to mention it as static, like this. Otherwise, if you don't write anything, the default is non-static. That's why the default is non-static. Is that okay? Hello?
Yes, sir.
So now
Yes.
up to this part, is it fine? So next, which statement will be executed after this? Cout. This cout main, this will be executed. After this, it will be executing this much. I mean, this malloc statement, right? So when it executes this one, what do you think? It is making a request to for a dynamic allocation. Where from it will be getting the space? Size of int. So 4 bytes or maybe 2 bytes, whatever. Where from it will get the space? From the heap. And what I say now PM should be pointing to that newly allocated location instead of pointing to this one. So once it is getting allocated, the address of this will be stored here, and PM is pointing to this one. Are you getting the thing? Hello?
Yes, sir.
It's something like you are in the, so you have got your friend in the foreigners hostel, and he knows your address. You are the CR, so he knows your address. So he can point somebody. Okay, you go to okay, CR's room is there in that hall 5, something like, or hall 10, or maybe some other halls. So it's something. So earlier this PM was pointing to somebody within the same hostel. Now the PM or this person, this student is pointing to somebody in some different hall. Something like it is really possible, right? So the pointer variable is in the stack segment. The pointer variable itself is hosted in the stack segment, but the location that it points to is in the heap segment. Are you getting this thing?
Yes, sir.
So now when it executes a function, so this function means it copies the value of LXM into this lxf, right? So when it enters this function, what happens now? Whatever was local to this main, it still remains because main is not yet complete, right? It remains there, but you are going to enter in this, you are going to execute this function, this one. So where are there any local variables declared within the function? Non-static local. Here in this function, non-static local. Are there any such values? What is this? This is, what is this lxf? Is this static, non-static, local, global? What type it is?
Local.
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 Local. Non-static. What about this PF?
Non-static local.
Non-static, and this PF also is non-static local. So is there any other variables that is defined here? No. So these two will be, you see, these two will be allocated here in the stack. So this way it is called a stack. So on top of the local variables corresponding to main, because main called function, so all the local variables of function also got, you know, pushed into it, and they will have some space occupied by it. But what about the static one, lsx underscore f, where it will be allocated space?
Data.
In the data segment, because no matter what it is, if it is a global static or local static, it will be allocated space in the data segment. And okay, one point I just forgot to mention, this global variables, you see global variables, simple global or static global, where it will be stored allocated space from, this global to this also will be in the
Data segment.
in the data segment. And here when it was main, it was a local static, so local static also was hosted here. So that's why when before you have called function here, you had three variables allocated in the data segment. One is because of this main function static, global static, and this simple global variable, non-static variable. Is that okay? So now when you are here inside, so by the time this static also has been allocated, so this is what lx underscore f, this one. Is that now fine? Can you visualize the allocation that is taking place?
Yes, sir.
So now see out, we know that something will be displayed, it will be quite fine. But now when it is calling this malloc, then again it is requesting 2 bytes of 4 bytes of space. Where from it will be allocated?
Heap.
Again from the heap. And this pf, that means this function's pf will be pointing to this one. Now when you are within this function, even though it is in the stack frame, but this is not accessible, right? So this is not accessible here because you are not within the scope of main. That is what it means. So that's why if you would like to have access to the contents of this, you have to pass it. lxm, you have passed it, and you have copied in the local variable lx underscore f, and through that you are using it, because only this much of the stack is active. So this is within the scope. Okay, so they are all alive, but this is within the scope. And you cannot really access lsx also. This lsxm, can you access this? Being here, can you access this? This is local to main. This static is local to main. So this function cannot access this also. So although it is available in the data segment, it is not within the scope. Okay, is that fine?
Yes, sir.
So now once it is done, now it calls, then this calls again function nested. It's a nested function within func. So this it calls, and here there is one more. What is this?
Local non-static.
Again you see, so there is a stack frame for this main, there is a stack frame for func, and there is a stack frame for function nested, which has this declaration and there is no other declaration. So they will, after giving cout, it will return back to where it will return back after getting this done. It will return back here, right? So what is going to happen? What do you expect when this control returns back from function nested? What is going to happen?
Function will end, sir. Last state.
No,
Function
in
will
terms of the memory, what is going to happen? What type of changes that you will feel? We'll see here. Function nested is gone.
That local variable will be deleted, sir.
So this will be, you see, saw the change. This goes off. Why? This is no longer required. So that's why. So there is a use of stack. So you already earlier learned in the data structure class that is a use of stack. So the sequence of function calls, the stack is used, and this basically the stack segment is used here. Is that fine? So when it is about to return from the func to the main, what is going to happen now? Returns here. What it happens now? Can you see what happens? It pops out what?
TF and LX. LS.
Okay, but one mistake I have made. LSX underscore f. It will remain there, right? So this is not popped out, but you cannot access it once you are outside this function. You cannot access it. It remains there. So now that is the end. So everything has ended. So once the return the control comes out of the main, then what happens? These two gets popped out. Is that fine?
Yes, sir.
Now can you see something that has happened here? Something that we don't want. When it popped out from this one, I mean when it returns from this one, the space allocated in the function which was in the heap. Now can there somebody is there some other pointer through which you can access it?
No, sir.
Of the microphone, I don't know whose it is. I mean, if you are answering, if you are interacting with me, then probably you can't help. But otherwise, if it is not the case, switch it off. I mean, if you are interacting, then yeah, we can tolerate the noise because some interaction is going on. So can you see this? So if I am here, what has happened? The memory allocated in this function that is here, is there any pointer which can take us to that location?
No, sir.
So what is the problem? So it is there, but it is now garbage. Garbage means what? Now anybody, if somebody accesses it, it is of no use because it is not through a valid pointer you are getting to that. So this is what is called garbage, and all such garbages which are left, it's like abandoned, and the contents of that location is also not important to us, and you cannot probably use it also, because if you again call malloc at this point, the memory management module will make sure that, so to the memory management module, this location is allocated. See the point, this is allocated, but to the programmer you cannot reach to this location via some valid pointer. So that's why it is a garbage. So garbage is something that is there, it's of no use, right? And this is what is known as garbage collection. So garbage collection means you have to, so how to remove the garbage from it? What is the mechanism to remove the garbage?
Free, sir. Free.
We have to call the
Free
function, right? So the free function is used to deallocate. So free is meant for deallocation. So like malloc allocates, free deallocates. So where should I call free to get it removed, to clean the garbage?
Inside func.
So inside func, maybe here before you are leaving within a function, whatever you have allocated within a function, you know that once I am leaving from the function, these are of no use. So before you leave some from a function, you should make sure that you free all the elements that you have allocated dynamically in the heap. Otherwise it will be just a heap of garbage, and if you keep on asking for malloc, all those garbage allocations will be treated as allocated by the memory management module, and it will not be allocated to you. So at some point of time, what you will see that there are enough space which is unused, but the operating system is unable to allocate space for you if you request for more, right? So you can make a small experiment within a for loop within a kind of infinite for loop. Say for example, you can give a value that how many times it is allocating. So if you allocate say 10,000 bytes at a time, so if you allocate and free, it goes on forever. But if you keep on allocating and then exiting without deallocating, you find that after a certain while it will be segmentation fault because it stops. I mean, out of memory or out of heap. Sometimes uh, some kind of comments like this will appear. Got the point? So this is the importance of garbage collection and the importance of free. So you cannot just keep on allocating space. It's always a very good practice to always make sure that all that what you have allocated in this function gets deallocated. Maybe there are multiple free statements that you have to write here in the main also, but in the main it is not that important because in any case if the program terminates, the operating system will take out everything that has been allocated to you, right? All these block spaces, segment spaces will be made free. Okay, but for other functions not in the main, you have to basically deallocate. So you should write here free pf, right? Are you getting things?
Yes, sir.
All of you, are you getting things? Others?
Yes, sir.
Yes, sir.
Yes, sir.
And this is
Yes, sir.
extremely important because without knowing the memory layout, writing codes, it is something like so because yeah, these days you are in a era of Python, so you really don't care what is happening inside, but you need to bother about because sometimes if you are given with a very large and very complicated application which demands a huge space, memory space, and it demands fast execution, then probably you have to get back and think that whether I can write something from the scratch in C or C++ instead of using a Python code. So that's why Python may not be, I mean, it's good for writing developing fast applications, but it may not be very efficient code that you require. I mean, sometimes you require very fast execution, and there C and C++ can help you. Okay, so too much of abstraction is sometimes not desirable for very robust applications or very that demands speed. Memory also you have to know, but definitely Python also internally manages the garbage cleaning and all this. But again, if you can do it of your own, you know that what I am doing and what I am cleaning, what I am having, and all this. Okay, so before I get into the dynamic memory allocation, I'll take another half an hour. Is that okay, or it will be difficult for
So
you?
actually, no, so actually we already had two more classes before it, and those, I mean, both of those had extended at least 20 to 30 minutes. So, I mean, a lot of people among us don't have enough data to continue that for that. So,
Okay, okay. Okay, fine. Then, because I thought of talking about dynamic application. Okay, the one thing is, before I stop this class, just 2 minutes. Uh, what do you interpret about the void data type or void pointer? Just that the last concept. What is void?
that doesn't return anything.
No, no. What is void? What is void?
Nothing.
Hmm?
Nothing.
Is it nothing or is it? I
Sir,
mean,
no
yeah.
defined return type is required, sir. So, like, there is no compulsion to return something, sir.
Can you interpret what void is from this?
So, like, also, like, one size fits all.
Yeah, it's something like the generic, right? So it's like a so void type is something like what I would say. It's like a sari or dhoti. So it never matters how tall you are, how short. So do you ever talk about the size of a sari or size of a dhoti? You don't, right? But for trousers, we need to say that what is your size and all this. So it's a generic type. So generic means you can mold it to any shape. So void pointer is also something like this. So void pointer means you can basically cast it to any type. You can cast it to integer pointer, you can cast it to float pointer, you can cast it to character pointer, something like so. Void is basically, it is not nothing, but it is Rather it is like everything. You can have anything out of it. It's generic. It's a generic type. So whenever we have nothing to specify, we really don't know what is going to what will be the data type. We really don't know. Then it is better we specify it as void. Is that fine?
Yes, sir.
So that is void is. So void pointer is also like that. So void pointer is just like a DAO. So you can give it any shape. So if you cast it, it can take any of the shapes. But otherwise it is just like it has no shape. So but you can mold it to any shape. That is the point. So this is important because sometimes in many cases we really don't know what the type will be dealing with in real time. So we just define it as void, return void, or so that's why in malloc is a single function which is used to allocate space for integers, floats, character, no matter what you have. So how to manage it? So the only way thing is a malloc, okay, it allocates the space, but it returns void type, void pointer. So that means now accordingly you can mold it to any shape. So you can, so molding means if this is a void type, so now it has got 20 locations, so you can make it to store 20 characters, or you can use it to store 10 integers, something like this. So it's up to you. So once you mold it or cast it to a int asterisk or float asterisk or character asterisk, you can use it in that way. Otherwise, because why it is required, because malloc is the only function which is required, which is used to allocate space for any type of data, integer, float, character. So the only thing is it should be returning void type. Otherwise you have to probably implement 4, 5 or many multiple malloc types, malloc int, malloc float, malloc. So that is not possible, and that is not provided in the by the compilers. Okay, so in the next class we'll be talking about the dynamic memory allocation on C++. We'll be talking about new delete, and yeah, this will be the just